Do not copy. Our programs are covered by registered U.S. copyrights. They may not be duplicated or copied. Willful infringement constitutes a felony punishable by fine and imprisonment. Civil remedies include statutory damages of up to $50,000 per offense, plus plaintiff's attorney's fees.
Semiconductors Explained. Part 2. Diode Theory.
In the first part, you were introduced to some basic principles of semiconductor theory.
You saw how the unique characteristics of semiconductors have made them a cornerstone of electronic technology, despite the fact that they are poor conductors and poor insulators. You were introduced to concepts of electron flow and hole flow within the crystal. You saw how pure silicon can be doped to form either P material or N material. You also saw that a junction diode can be created by doping a silicon crystal with P material on one side and N material on the other.
In this part, the theory behind the operation of a junction diode will be examined. You'll see how it behaves when unbiased. Then, after a voltage has been applied, you'll see how a junction diode can be either forward biased or reverse biased. Finally, some common diode specifications will be introduced. Let's get started. We'll look first at an unbiased junction diode. An unbiased diode has no external voltage applied to it.
Look at this graphic representation of what a PN junction looks like at the moment that the N and P materials are combined. Holes in the P material are designated with plus signs, and electrons in the N material are represented by minus signs. Bear in mind that from this point, only the majority carriers will be shown. At this moment, each atom has exactly the same number of positively charged protons and negatively charged electrons. This results in a neutral or balanced state.
However, the diode remains this way only for an instant because something interesting happens at the junction as soon as it's formed. Let's examine an energy band schematic to see what happens.
Remember, both the holes and the electrons are free to move about in random fashion. With so many holes available, the free conduction band electrons in the N material automatically diffuse across the junction, quickly falling into valence band holes in the P material. When this happens, the hole disappears and the electrons become valence electrons at a lower, more stable energy level. You'll recall that this process is called recombination. It's important to note that holes will not diffuse across the junction. Holes exist only in the valence band, not in the conduction band. A hole can be filled by a free electron, but it cannot move up into the conduction band to meet the electron. This recombination of P and N material produces an area at the junction called the depletion region. There are essentially no majority carriers within it, no free electrons, and no holes.
Let's slow this instantaneous diffusion down so that we can follow it step by step.
When a free electron in the N material diffuses across the junction, it leaves behind a positive ion. An ion is simply a charged atom. It's one which is no longer electrically neutral because it has either gained or lost an electron. The atom in the P material which picks up the electron in turn becomes a negative ion. Each time an electron diffuses across the junction, another pair of ions is created. As the depletion region grows, a difference of voltage potential builds up, creating an electrical field. This happens because there are positive ions on one side of the junction and negative ions on the other. The voltage associated with the depletion region is referred to as the barrier potential. Eventually, this electrical field becomes large enough to prevent further diffusion, and the depletion region stops growing.
At room temperature, this barrier potential is approximately 3/10 of a volt for germanium diodes and 7/10 of a volt for silicon diodes. Although these voltages are small, their presence establishes the unique operating characteristics of the diode. After the initial diffusion is finished, when a free electron from the N material tries to pass through the depletion region, it's repelled by the newly formed column of negative ions in the P material because like charges repel each other. At the same time, that very electron is also attracted by the newly formed column of positive ions because opposite charges exert an attractive force upon each other.
So far, you've seen what happens in an unbiased junction diode with no externally applied voltage. Now let's examine how it behaves under the influence of an applied voltage. This is called biasing the diode. It can be done in one of two ways, either by forward biasing or reverse biasing.
In order to forward bias a junction diode, the negative side of the battery is connected to the N material, and the positive side of the battery is connected to the P material. To reverse bias a junction diode, the connections are reversed. The positive side of the battery is connected to the N material, and the negative side of the battery is connected to the P material.
Recall the schematic symbol for a diode and how it correlates with the pictorial. The N side of the diode is called the cathode, and the P side is known as the anode. Let's substitute this symbol into the simple circuit diagram you've just seen. Keep in mind that this is for illustration purposes only. A diode would never be placed directly across a voltage source because it would burn out. Remember, when the diode is forward biased, the negative terminal of the battery is connected to the cathode. When it's reverse biased, the negative terminal of the battery is connected to the anode.
Let's see how the junction diode responds to an applied voltage. We'll take a closer look at a forward bias diode using a schematic.
Once the depletion region is formed, the barrier potential inhibits any further movement of electrons across the junction. But the battery now creates another force. The positive side of the battery now repels some of the holes in the P material, sending them toward the depletion region. At the same time, the negative side of the battery repels some of the negatively charged electrons in the N material, also sending them toward the depletion region. The negatively charged free electrons neutralize the positive ions in the depletion region. At the same time, the holes that were repelled toward the depletion area act like positive charges and neutralize the negative ions. With all of the ions neutralized, the barrier potential is essentially overcome, and the depletion region disappears. Current can now flow from the external circuit through the diode. This flow is sustained because the holes and the electrons recombine at the junction. Conduction band electrons from the N material fall into the holes in the P material and travel through it as valence electrons. A forward biased diode, then, simply behaves like a conductor. You can think of it as a closed switch, although in actuality there must be enough force applied to overcome the effects of the barrier potential. Silicon diodes require at least 7/10 of a volt of external pressure in order to conduct current. Beyond these voltages, the forward biased diode will offer little resistance to current flow.
A reverse bias diode behaves very differently. Let's see why.
Recall that in a reverse bias diode, the negative side of the voltage source is connected to the anode, or P material, while the positive side is connected to the cathode, or N material. Let's see what happens after the depletion area is formed. The holes in the P material, since they act like positive charges, are attracted by the negative terminal of the voltage source. They are drawn away from the depletion region and toward the end of the semiconductor. Simultaneously, the electrons in the N material are attracted by the positive potential of the voltage source. They are also drawn away from the depletion region. As the holes and electrons move away, they leave more ions behind. This widens the depletion region. The greater the reverse bias, the wider the depletion region, and the greater the barrier potential. The depletion region will continue to expand until its barrier potential equals the applied reverse voltage. Keep in mind that this actually takes place in an instant. The expanded depletion region behaves like an insulator. It blocks the flow of electric current. In this respect, a reverse bias diode acts like an open switch.
While the switch analogy helps to point out the meaning of forward and reverse bias, it's important to realize that the diode is not a perfect device.
When forward biased, there is still a small amount of reverse current due to the movement of minority carriers. When reverse biased, there is still a small amount of leakage current that is able to make its way through the depletion region.
Normally, this leakage current is negligible, but under the stress of circuit operation, a diode can sometimes become excessively leaky and should be replaced. The main principle of a junction diode, then, is that it conducts current much better in one direction than in the other. Like any electronic component, the diode has maximum voltage, current, and power limits within which it can be safely operated. Let's take a look at 3 of these specifications.
One important specification is known as the maximum DC forward current. This refers to the maximum amount of current that a forward bias diode can safely handle. Values for this specification often run in the range of 1 ampere of current. Since the diode can burn up if this limitation is exceeded, a current limiting resistor is usually placed in series with the diode. While there are some diode circuits, such as rectifiers, where this would not be necessary, it's important for the technician to know when and where current limiting resistors are required.
A second specification to be aware of is called the peak reverse voltage or peak inverse voltage. This value refers to the maximum level of voltage that can be applied to a reverse biased diode. If this limit is exceeded, the diode will break down and begin to conduct current in the reverse direction. Current will actually be forced through the depletion region. This can weaken the diode and shorten its life. If the power rating of the diode is exceeded in the process, the diode will burn out.
A third specification is the maximum power dissipation. This can be understood by recalling the power formula P equals I times V. The power dissipation of a diode is the product of its voltage and current at any moment in time. The listed specification should not be exceeded. If it is, the diode will burn out. For example, suppose the maximum power of a diode is 1 watt. If the applied voltage to the circuit is 120 volts and the resistance R equals 240 ohms, then Ohm's law can be used to find current. 120 volts divided by 240 ohms equals 0.5 amps. Now, using the power formula, 0.5 amps times the voltage across the diode, 0.7 volts, equals 0.35 watts, which is less than 1 watt. This circuit is okay. But now R equals 60 ohms, with the power maximum still equal to 1 watt. Multiply 2 amps times the diode voltage. This yields 1.4 watts. Since this value is greater than the maximum power dissipation for this diode of 1 watt, the diode will burn out. This underscores the importance of selecting the right resistor value.
With all of these specifications, a certain safety factor, usually 2 to 1, is taken into consideration when selecting a diode for a particular circuit design.
Suppose, for example, that the current flowing through a diode is not expected to exceed 250 milliamps. The diode selected for this circuit should have a forward current rating of approximately twice that level. In this case, about 500 milliamps, or 1/2 of an amp.
Now that the basic theory behind the operation of forward and reverse bias diodes has been examined, and some important specifications have been presented, let's see how a diode's current and voltage characteristics can be analyzed. This can be done on a curve tracer.
The relationship between current and voltage is called the volt-ampere, or IV characteristic curve of the diode. Voltage is plotted along the horizontal axis and current along the vertical axis. Now, let's insert the junction diode in the test fixture. Be sure to close the safety guard before beginning to check the curve. Now we can look at the IV characteristic curve for the junction diode. Notice that beginning at 0 and moving gradually along the horizontal axis for the first few tenths of a volt, the current that flows through the diode is extremely small. As you can see, there is almost no vertical movement on the current axis. This is due to the opposing force of the barrier potential within the diode, a force which must be overcome before the diode is able to conduct current. As you learned earlier, that barrier has an effective voltage potential of 7/10 of a volt for silicon diodes. However, once this voltage is exceeded, current through the diode increases rapidly. The sharp turn in the curve at this point is known as the forward knee. Beyond the knee, the current will increase rapidly because once the barrier potential has been overcome, the diode will behave very much like a closed switch. In actuality, the diode does have some resistance, but this value is normally negligible.
The IV characteristic curve for a junction diode also shows the operating region when reverse biased. With the scale changed to 50 volts per division, you can see that this region extends on the left from a point called the breakdown voltage, labeled B sub V, to the forward knee voltage. The breakdown for this diode begins at about 130 volts. It's important that you be able to read an IV characteristic curve.
As you study semiconductors, you'll often hear the junction diode referred to as a nonlinear device. This means that the changes in current are not proportional to the changes in voltage. The opposite of nonlinear is linear. A resistor in which changes in current occur in direct proportion to changes in voltage is known as a linear device.
If each pair of corresponding current and voltage values for a sample resistor are plotted, they will form a straight line. This is why a resistor is called a linear device. But the volt-ampere relationship of any nonlinear device, such as a junction diode, will always form a curve.
One of the most dramatic applications of the diode is within the context of an AC circuit. Remember that in an AC circuit, the direction of current flow changes at some regular interval.
Another way of describing this change in direction is to say that the polarity of the source reverses every half cycle, which you can see on this oscilloscope. The midpoint between the upper and lower peaks of this waveform is the zero reference. Current flows in one direction through the circuit during the positive half cycle, and then flows in the opposite direction during the negative half cycle. When a diode is placed in an AC circuit, it will be forward biased for a half cycle, allowing current to flow, and reverse biased for the other half of the cycle, blocking the current flow. The diode converts the AC signal to a DC signal, which flows in only one direction. When a diode is used in this way, it's called a rectifier diode.
This process of rectification is the principal feature of power supply circuits. Let's stop here and review what you've been shown in this part.
The basic theory behind the operation of a junction diode has been examined.
The differences in the way it behaves when forward biased and reverse biased have been shown.
common specifications for the junction diode were presented.
Finally, you saw its volt-ampere characteristics on a curve tracer.
In the next part, you'll see specialized types of diodes, including Zener's and light-emitting diodes. Before going further, though, you may want to review this part one more time, in case you have any questions.